Hey everyone! Today I thought it might be quite interesting to give you an overview of the different kinds of two-dimensional materials there are. Some that I work with directly and others that are out there in the world. Some of these you will have heard of already, mainly if you've seen my other videos, and some are really brand new stuff on the research scene. So without further ado, let's dive in and look at the thinnest sheets nature has to offer. Graphene. Graphene has come up several times before. It consists of sheets of carbon atoms arranged in hexagons, and is very electrically conducting, strong and transparent. We can produce it by separating the layers in naturally occurring graphite, or we can grow it using chemical vapor deposition. The range of properties graphene has makes it very versatile in nanotechnology. It can be used to make simple electrodes that transmit light, it can be added to reinforce plastics and make them conductive, and it can be used as a support for growing living cells, to name just a few ideas. Graphene has an extremely high surface area per unit weight too, which makes it very useful for electrodes in batteries or for sensing tiny amounts of gases in explosives detectors. A lot of effort and money is being poured into graphene at the moment, and it is by far the most technologically developed compared to the other 2D materials. This is useful, as many of the processing routes and much of the understanding can be transferred when trying to use the other materials. Graphene-containing products are likely to be appearing over the next few years, and there is projected to be a huge boom in the market for industrial graphene production. Boron Nitride. As the name suggests, instead of carbon atoms, hexagonal boron nitride is made of boron and nitrogen atoms, which are found either side of carbon in the periodic table. I find this material to be a real oddity, because it is almost structurally identical to graphene in every way, yet it's a white electrical insulator rather than a black electrical conductor. It is so similar, in fact, that some call it white graphene. Just like graphene, boron nitride is an exceptional thermal conductor and is very, very strong. So it finds a lot of uses as a reinforcing filler in composite materials, where the conductivity of graphene isn't necessary. It is also useful as a surface for assembling other nanomaterial structures on. One of the big differences is in how it is produced. While graphene can be made from graphite, which is naturally occurring, boron nitride powder is a fully synthetic material. It is still widely available though, and almost all of the processing methods that work for graphene work for boron nitride too. It will probably form a part of most technologies that rely on combinations of multiple nanomaterials, like printed circuits. TMDs. Transition metal dichalcogenides are a family of two-dimensional semiconductor materials. They are made up of a layer of transition metal atoms, like tungsten, sandwiched between two layers of chalcogen atoms, like sulfur. These materials are extremely versatile, especially in electrochemistry. They are great catalysts in reactions like hydrogen evolution, which is the process of splitting water molecules into hydrogen and oxygen. Being able to split water with a very high efficiency is an absolute necessity for being able to make hydrogen fuel cells, which are already being used to power public transport in certain parts of the world. Some TMDs are also really good for making supercapacitors, which are likely to replace batteries in some applications in the coming years. They have the advantage of charging times associated with traditional capacitors, which is in the seconds, as well as the energy densities associated with conventional batteries. This could lead to a real revolution in the way we power our mobile devices, especially if combined with things like inductive charging pads. Simply hold your phone here for 30 seconds to charge, then on your way. The member of the TMD family that has been most studied to my knowledge is molybdenum disulfide. This is a naturally occurring mineral, which has actually been used for many years as a dry lubricant in engine transmissions for cars and in aircraft. Black phosphorus. Much like graphene, black phosphorus is an elemental 2D material. Its atoms are arranged like a sheet of corrugated card, which means that the material is much more rigid in one direction than the other. Like the TMDs we just looked at, black phosphorus is a semiconductor, which makes it good for detecting light as well as making transistors. The main problem is that black phosphorus degrades quite quickly in contact with both air and water. This makes it very difficult to process, and not really ideal. To protect it, people tend to trap it between layers of other materials, or coat it with polymers which slow down the process of degradation. Black phosphorus is an allotrope of phosphorus, just like graphene is an allotrope of carbon. It is made by heating up white phosphorus, a different allotrope, under immense pressure. This is a lot like how natural graphite forms in the Earth's crust. It was first prepared in 1914, but only recently have people looked into separating out the individual layers and looking at their properties. Due to the difficulty in preparing and processing this material, I doubt that it will see many commercial applications in the immediate future. But then, it wasn't long ago that people were saying the same about graphene. There are some other materials, like MXenes, which I will cover another time, as there's quite a lot to say and this video is already getting on the long side. However, I hope this has at least given you a broad appreciation for how many different 2D materials there are in the world, where they come from, and what they're useful for. See you next time! Thanks for watching, everyone. If you like what I do, please consider supporting my work via my Patreon page, where you'll have access to a range of in-depth discussions on the physics, chemistry and engineering of nanomaterials. If you'd like regular updates, please subscribe and like the video. It helps so much, and I look forward to talking to you again soon.